of Aeronautics of the United States Navy presents successful factory methods of the aircraft industry for the benefit of American manufacturers who have converted their peacetime plants to the manufacture of wartime planes. The ability of an airplane to hold together in flight the very lives of its passengers and crew depend on the skill and integrity with which the riveting and bolting is carried out and inspected. There are 78,000 rivets in one well-known fighter, more than 130,000 in a medium bomber, and about 400,000 in a four-motor plane. Although most aircraft factories buy their rivets ready-made, a few plants operate their own machines to turn aluminum alloy wire into rivets of various types and sizes. The machine is almost entirely automatic in operation. Aluminum wire is fed in from a reel, and the machine measures off a predetermined length. This is cut off and moved into a die where a double impact from a reciprocating hammer flattens and forms the head. In order to make this action visible, the machine as shown here has been slowed down. But when operating at normal speed on small rivets, the output is as high as 450 rivets per minute. The same machine may be used to make a wide variety of lengths, diameters, and heads by changing the die, altering the setting. Head markings identify the four different aluminum alloys used for standard aircraft rivets. The A17ST alloy is identified by a dimple in the head. It's known as the AB rivet. It possesses ease of driving and good strength characteristics. The 2S material has no marking and is known as Type A rivet. This soft aluminum rivet is used for temporary assembly and non-stress joints. These two types do not require heat treatment. The two remaining types are the 17S alloy, known as Type D, and identified by a raised dot in the center of the head. And the 24S alloy, identified by two raised dashes in line, known as the Type BD. These two types require heat treatment, refrigeration, and use within 30 minutes after removing from the icebox. Four important types of rivet heads are used in aircraft manufacture: flat head, round head, brazier or semi-brazier head, and countersunk or flush. There is an increasing tendency to simplify riveting by the use in nearly all cases of two types only: the round head or an equivalent, and the flush head of one sort only. On airstream surfaces, some firms use brazier or skin rivet. Drag is low with this type head. Flush rivets, however, reduce drag still more and can advantageously replace the modified brazier head entirely. They are being used more and more in modern streamlined planes. The second head is formed on the rivet by the hammering pressure of a die or set placed in the head of the rivet gun, while a heavy bucking or dolly bar is held against the shank. The vibration of the blows on the head causes the shank to become flat. The diameter of the new head should be from 1 1/3 to 1 1/2 times the shank diameter, and the height from 40 hundredths to 65 hundredths the shank diameter. Rivet set and bucking bar must be held firmly in a straight line, or the head may not form evenly. The inertia of the bucking bar provides the force that upsets the rivet. The structure in which the rivet is being driven must deflect with each blow to provide the necessary movement. Bucking bars may range in weight from 3/10 of a pound to as much as 12 pounds, and the size and shape depend on the rivet diameter and the space available. Proper riveting is accomplished only when the rivet set is of the right size and shape. Here is one that is undersized. The result is a ringed and weakened rivet. When the rivet set is too big and too deep, the results are a weak joint, ringing on the skin, and a loose rivet. If the set is too large and shallow, the head is flattened, which may break the protective coating, causing future corrosion. Rivet sets are indented for the heading of round and brazier head rivets, while for flush and flathead rivets, the driving end of the set is flat. The modern high-performance airplane is usually flush riveted with countersunk rivets on the airstream surfaces. For light-gauge material, a depression or dimple is made around the hole by counter-pressing the sheet before assembly. If the hole has been punched, burring will usually be essential to avoid cracks during the dimpling operation. Dimpling may also be done in a squeeze riveter by means of specially shaped sets. For heavy gauge stock or extrusions, a countersinking tool is used to bevel the edge of the hole. In this case, a special countersinking machine is being used. Countersinking may be done by hand, using a tool with an outer sleeve which limits exactly the depth of the bevel. In locations where the heading of rivets is difficult, the simplest solution is the use of special blind rivets. But extreme ingenuity is demanded in the development of bucking tools which will reach almost inaccessible placements. The operation shown here in a wing assembly has been made possible by the development of a pneumatic bucking tool of special construction. The bucking tool takes the form of a flat plate which can be moved outward by air pressure to buck the unformed end of the rivet. This tool, known as the mouse, can be inserted in locations where any other type of tool would be useless. The use of such a tool makes it desirable to be able to inspect all rivets carefully. To this end, an ingenious instrument has been developed known as the foresight. It consists of a low-power telescope. This is connected to a long, hollow tube. At the far end of this tube, a housing with an open side is attached. In this housing, a mirror is placed. Behind this mirror, an electric bulb is located. Interior inspection of rivets can efficiently be made with this bore sight. The light from the bulb illuminates the rivet to be inspected. The image of the rivet is reflected by the mirror and transmitted through the hollow tube to the operator's eye. The operator is able to inspect the formed heads on all rivets with perfect visibility, and any defective rivets may be immediately drilled out and replaced. When the unformed end of a rivet is not accessible for bucking, some type of blind rivet must be used. One form of this is the explosive rivet, which uses a small charge of explosive to spread the end of the hollow shank. In this case, pads of latex are being fastened inside a bomber tank door. The rivets are inserted in holes in the retaining sheet. Heat is used to explode the rivet, forcing the shank back against the plates, making an instantaneous grip. In many cases, where not even special bucking tools can make possible the use of normal rivets, the mechanical blind rivet is employed. The rivet itself has a hollow shank. Inside this shank is a snugly fitting rod with a bulb-shaped end. The rivet is inserted in the hole. A tool, somewhat like a nail puller, grips this rod and draws it up. The tip of the rod is drawn into the hollow shank, mushrooming it out and forming the inner rivet head. The projecting rod is trimmed off, leaving an attachment of high consistency. The action of forming the rivet head tends to draw together the sheets being fastened, and slight variations in sheet thickness are automatically compensated for. A closely allied form of attachment is that shown here. This is similar in shape to an ordinary rivet, but is hollow and is threaded on the inside of the shank. The threaded mandrel of the upsetting tool is screwed into this shank. The rivet is then When placed in position, the pullback of the mandrel mushrooms the shank, fixing the rivet in place. The mandrel is then removed. This rivet fills a double function, as attachments can be added by using the threaded shank for receiving screws or bolts. It is used principally in the leading edge of wings and control surfaces for the attachment of de-icer-booms. The compression riveter differs from the riveting gun in that it forms the head by a squeezing or compressing action instead of distinct blows. It delivers results of great uniformity and is usually the most rapid method of heading rivets. The simplest type of compression riveter is the hand squeezer. Special riveting setups do not always demand expensive and elaborate equipment. Many jobs can be conveniently carried out on an ordinary pneumatic squeeze gun clamped in a vise. Such guns can also be set up with a foot pedal release, leaving the operator's hands free. In these examples, we see the riveting of a carburetor air scoop, of an air filter, a tail wheel cone. The one-shot or single-impact riveting gun is designed to drive the rivet with a single blow. It comes in several sizes for different rivet diameters. Under suitable conditions, it is one of the fastest methods of riveting. Repeating guns have the advantage that the degree of upset applied to a rivet may be regulated by the number of blows as well as by alteration of the air pressure. The corner riveter is similar to the ordinary repeating gun, but has the set placed at right angles to the tool. It is used in corners and in close quarters. Similarly, the die may be offset for better accessibility. On the modern assembly line, where the work moves forward steadily, it is important that riveting be carried out expeditiously. In this instance, a considerable saving of time is effected by suspending the drill and the riveting gun from spring-loaded reels overhead. In this way, the operator loses no time groping about for tools. Efforts are constantly being made to simplify and lighten the work of riveting, particularly in view of the necessity of employing an increasing number of women for the job. A typical example is this self-bucking riveting gun, which makes it possible to rivet flat sub-assemblies without a second operator to buck the rivets. The gun is suspended from an overhead monorail so that the operator guides the gun but does not have to support its weight. This hydraulic squeeze riveter exerts a pressure of 5 tons, yet the manner of its support relieves the operator of any unnecessary fatigue.